Hello folks! Well, this time around we want to take a look at dynamic memory issues. So looking at what has to take place when you've got programs that dynamically request and release chunks of memory. So usually this is the idea of the heap when we're talking about the use of memory in a program. So I want to consider lots of different aspects of this today, and then in the next couple of videos we'll be looking at implementation techniques to actually make this work behind the scenes. So just at a high level view, again, we're looking at programs that request chunks of memory as they're running. So they figure out how much space they want, they ask for it, somehow the system goes off and finds it and gives it back. It gives back a reference to it or a pointer to it. Eventually that space has to be released and returned to the pool of free space. This could happen either because it's a specific request by the programmer, so the C or C++ style of mallocs and news type of thing where they directly ask, could I have this please? Or it could be implicit requests where you create a new object in an object-oriented language, or you create a new list in Lisp where all of this stuff is automatically created somewhere out on the heap. So whether it's explicit or implicit, this is still taking place as the program runs. You've got to be able to get at the resource once it's created. You need to be able to free the resource once the program's done with it. And then you need some kind of safeguards to keep this all from blowing up in your face. So one of the big philosophical questions for a language is, how do you divvy up all of these tasks? How much of it is made the responsibility of the programmer, and how much is handled by the system, especially with regards to the safeguards, right? How much of that is just left to the programmer to protect themselves, and how much does the system actually protect you? So on that note, I just wanted to kind of touch again on the distinction between references and pointers. Right, in a pointer-based system where the programmer is actually playing with memory addresses and where they can actually see the virtual memory address of something, that's a much different situation than in a language that uses references, where there is this kind of indirect referral to an item, but the programmer never sees the implementation and they never actually see the memory address of the item. So if you're looking at references for heap access, then all of the implementation details are hidden from the programmer, and pretty much the responsibility for everything then lies on the system side, right? The system side is entirely taking care of the allocation, the deallocation, the safeguards. Whereas with pointer-based systems, an awful lot of the control and an awful lot of the responsibility is turned over to the developer, to the programmer. And as you know from your own experiments with C and C++, this can be a good thing and this can be a bad thing, right? Powerful but risky. One of the things we'll look at in a few days is the idea of smart pointers. So smart pointers are an attempt to kind of bridge the gap between these two things. It's almost like creating a reference-like system that's available to programmers in a pointer-based language. So we'll come back and look at smart pointers a little later on. Whichever way you do this, again, the system needs to be able to maintain some kind of pool of what memory is available to be used. And as requests come in, it's got to be able to search that pool, find an appropriate chunk of memory, remove it from the pool, give access to the program, and then when the program's done with it, it's got to be able to recapture that space and return it to the pool. And it needs to be able to do all of this sort of safely and efficiently. So in the next couple of videos, we'll actually look at implementation approaches to do this. So if we are dealing with a pointer-based system where an awful lot of the control is in the hands of the programmer, there are, of course, a whole bunch of things that can go wrong. So I just wanted to touch on a few of the key ones here, and we'll keep them in the back of our mind when we're looking at particularly when we get into looking at the smart pointer side of things that's trying to solve a lot of these problems or prevent a lot of these issues. So wild pointers, here we're just talking about cases where a programmer is using a pointer that hasn't actually been initialized. It could have any random value in it. It could point anywhere. So they're using a pointer as if there was dynamically allocated memory at the other end of it, but who knows what's actually on the other end. cases where the pointer actually contains an invalid address. Now, it could be invalid for a whole bunch of different reasons. It could actually be outside the range of accessible memory somehow. It could contain a null pointer, for instance. It could violate the alignment boundaries, right? You might be trying to refer to a double at an address that isn't divisible by 8, or trying to refer to an int at an odd address or something along those lines. Or it could be invalid because it's violating whatever access permissions are in place on that particular chunk of memory. Maybe you try and write to a chunk of memory that's marked read-only somehow. So lots of different reasons why pointers could be invalid and cause you runtime issues. Dangling pointers, again, we should all be familiar with these by now. The idea that a programmer dynamically allocates some memory or requests it be allocated, uses it for a while, deallocates it, right? Says, okay, it's free, return it to the pool, but then sometimes later goes on and uses that pointer again as if they still had access to it, as if that memory space was still allocated. So now you're potentially writing into a chunk of memory that's been taken out of the pool and given to some other part of the application for use. Or memory leaks, the case where the programmer simply forgets to deallocate a chunk of memory or loses the last pointer to it. So we've requested a chunk of memory, but then overwrite the pointer to it, so we no longer have access to it, so we can't free it up. So it's essentially just wasted space now as long as the program continues to run. So in terms of the system side of things, right, the system has to take care of the allocation and release of the different resources, these chunks of memory. So it's got to be able to keep track of this pool of memory. When a request comes in, it's got to be able to go through this pool of memory, find a chunk that's an appropriate size, remove it from the pool, and give access to the program. Right? It's got to do that reasonably efficiently. When there is no longer a need for that particular chunk of memory, once the program is done with it, then the system's got to be able to take it, return it to the pool so that it can be allocated again for somebody else later. And it needs to be able to do these things quickly, but also to organize the memory so that it's making effective use of all of memory, of all of the available memory, so that we can give out as much of the space as possible in as flexible a manner as possible. So for instance, if we get a whole slew of requests that come in for little tiny chunks of memory, and this uses up almost all of the available heap space, and then gradually deallocation requests come in and lots of pieces of it are freed up, but those freed up pieces form little tiny fragments scattered across the heap. So maybe 50% of your heap, 50% of your pool is unused, but it's in all these little tiny chunks that are broken up by other chunks that are actually in use. So when a request for a big piece of memory comes in, you technically have the space available, but you can't find one chunk all in a row that's big enough. So one of the things that's important is finding a way to organize your memory pool so that you don't get this kind of fragmentation taking place. So we'll take a look in the next couple of videos at how we might actually achieve that. Then specifically on the collection side of things, where we want to go through and grab chunks of memory once they're no longer needed and return them to this memory pool, this is often referred to as the idea of garbage collection, right? Going out there, finding the chunks of memory that are no longer needed and returning them to the pool so that we can go out and use them. So we want the system to do this as soon as or as early as possible, really. Once the memory is no longer in use by the program, technically, we could wait until we actually needed the space before we went out and found it. So there's a few different approaches philosophically for how and when to perform your garbage collection. The eager approach is where we go through and say, okay, as soon as something's freed, as soon as something's no longer needed by the program, I want to recapture it and return it to the pool. So we'll take a look at an idea of using reference counts, keeping track of how many things are referring to a particular chunk of memory. And as soon as the reference count for something reaches 0, we say, nobody can get at it anymore, let's return it to the pool. So we'll look at this idea of eager approaches. Another idea is to just hold off on garbage collection until we actually need it. At the moment when we realize that we don't have enough space anywhere to service one particular request, then we'll turn around and say, okay, now I need to go clean things up and find some space. So if we take this kind of an approach, then the program is running faster up until then because we're not going through and spending time recapturing things, right? We're waiting until a moment when we go, oh, well, I don't actually have an available chunk for you. Now I'll go look for one. So this might actually take longer once we get to this point, but things might run faster than an eager approach up until then. So trade-offs either way. You could try and strike a balance between the two, where you say, well, we'll simply do periodic scans through the memory that's out there and recapture things when we do one of these scans. Or a sort of on-demand approach where when the programmer specifically makes a request or when the application specifically makes a request, then we'll run a sweep and do some garbage collection. So you could use any of these approaches or a hybrid approach, right? You might take a periodic approach, but if you hit the situation where it's needed, then you'll stop and do it then. But any one of these is a perfectly valid approach to doing this. Now, there is a significant impact to which philosophical approach you use. Right? You need some kind of data structure and some kind of memory overhead to keep track of the different pieces of memory that are and are not in use, right? What's actually been allocated and what hasn't been. What are the boundaries between these things? How do we refer to them? So there's going to be some extra memory space used just to keep track of all of the stuff that's out there and what is and is not in use. You've got the extra runtime when you actually do your garbage collection, right? When you're updating what is and is not in use, and to actually recapture stuff and return it to the pool. If you're going through sort of all of the different chunks out there in the heap and checking them all to see if there's anything out there that's no longer needed, you could have a significant delay at that point. So the delay that takes place when you run garbage collection can be significant. And if you've got a program that's running sort of close to real time, if you've got a game or if you've got an actual real-time system, a delay like that can be really significant, right? Your game might look like it's freezing or stuttering, or the program, the application might freeze for a moment, which, again, if you've got a real-time application, can be fairly serious. So which garbage collection approach you take determines when these impacts are felt and how severely, right? How much overhead are you using? When does the CPU overhead come in? Is it in little tiny chunks that are more or less unnoticeable, but they do kind of add up in the overall runtime of a system? Or does it periodically just stop and go, whoa, wait a minute, got to do garbage collection, and run through and do that? All right, so how much time it takes, when it takes that time, and how much control the developer has over when this happens varies a lot from language to language. So big implications for this, and what I want to do in the next couple of videos is look at how we might organize our pool of free memory to do this, and then some allocation and deallocation approaches, some algorithms to try and make this all work. So pick that up next time.